Hi there, this is Matt Heffernan, and welcome back to my channel. Today we're going to be doing a bit of a test between different 8-bit platforms, or in maybe more extreme terms, an 8-bit Royal Rumble. Oh wait, no, I'm sorry. Can't call it a Royal Rumble. That would be a copyright strike against me. I'll call it a Battle Royale. So I'm pretty sure that's in the public domain. So what we're going to do is generate some code. This is the first round. We're just going to be doing basic code. So we're going to look at the Commodore X16, of course, the dream computer that I've been generating a lot of content for over the past couple years, but also some classic 8-bit platforms, including the Commodore 64 and, of course, the Sinclair ZX Spectrum, which my latest series has been focusing on. So what we're going to do to test out these different systems to help compare them against each other in terms of some of their real raw horsepower is how quickly they can generate a very low resolution Mandlebrot Set fractal. So as we can see here on Wikipedia, Mandlebrot Set, it's probably the most famous of all fractals, at least in terms of how it is generated and how familiar it is, how iconic it is, and because it's definitely one of the more telegenic ones. In fact, going back to the very early days of the World Wide Web, the very first web page I remember going to, well, besides the homepage that I had at the computer science department at my university back in 1994, it had a bunch of links to it to just random sites because the web was brand new. The NCSA Mosaic just came out of the University of Illinois. Netscape hadn't come out yet, so it was extremely brand new. And one of the sites linked to from my university's computer science homepage, and I think then only the computer science department had a homepage, was a link to a French university that had some big computers that they were generating from what was, in 1994 standards, high definition fractal imagery. And at least and in some cases scaled down enough so that within a reasonable amount of time, again with 1994 bandwidth, be able to download those and display them on a terminal at the time. I was working on an old Sun Spark station, although it was a brand new one at the time. So going through all these pictures of the fractals, and at this point, having a computer that could generate a fractal in a reasonable amount of time at a high resolution was still pretty out of reach. But you could generate a low resolution one. And in fact, even on an 8-bit computer that is running at all of 1 megahertz, like the Commodore 64, can still generate a fractal. You're just going to have to wait a little longer than on a more powerful computer. And the nice thing is that our friends at Wikipedia, of course, the global hive mind, here on the Mandlebrot Set page, has put in a nice pseudocode algorithm for generating a Mandlebrot Set. And as you could probably guess, it's fairly simple in terms of the number of steps you have to do, the actual operations that are required. So basically, you have to define what your resolution is, what your X width is, and what your Y height is of the actual bitmap that you're going to generate. Of course, we're going to do a very low-res bitmap for all these platforms. We're going to be looking at 8x8 squares as our quote-unquote pixels for this experiment. And so what you want to do is then scale down that pixels. So you're scaling down the width to be going from 0 to whatever. And in this case, our lowest common denominator is unfortunately, it's the Sinclair ZX Spectrum. I know a lot of folks out there want to say that it's the most awesome 8-bit computer. Maybe not. In terms of graphics, there's some very significant limitations. And one of those is, of course, when it comes to the color. And you can only have different colors over this 32 by 24 grid. And so we also need to sort of sacrifice the bottom 2 rows because those aren't going to be able to stay up. So what we're going to do is a 32 by 22 grid of big, thick 8 by 8 big square pixels. so we need to scale those coordinates on the x-axis to minus 2.5 to 1, and on the y-axis to minus 1 to 1. So we're coming up with slices. So for our x width is 32, so we got 32 slices between minus 2.5 and 1, and for the y-axis 22 slices between minus 1 and 1, and so on. And then we go through this fairly simple loop where we only go through as many iterations as we need to. We're waiting to see if x squared plus y squared is waiting until that's greater than 4. Or we've hit our maximum number of iterations. You can see here in this pseudocode, it's showing, oh, we're going to go up from 0 to 1,000, so like 1,001 iterations. So no, we're not going to do that. Or actually, I guess just 1,000 because it has a less than there. So yeah, we're not doing 1,000 iterations. We are going to do up to 15 iterations because, again, lowest common denominator, ZX Spectrum, only have 15 unique colors. So what we're doing each iteration is we're calculating this x temp variable and taking x squared minus y squared and adding x0, which is the scaled coordinate, x coordinate, based on that minus 2.5 to 1. And then we are reassigning our y value to 2 times x times y, and then adding in the scaled y coordinate. And then now that we're done using the old x, we update x to the new value. We calculate it up here, and then we go to the next iteration. And we keep doing that until that x squared plus y squared is 4 or greater. And then based on the number of iterations that we went through, either up to the max or somewhere from 0 up to there, we then pick a color from a palette. In this case, we're going to be picking out of a 15 color palette. Again, ZX Spectrum, 15 colors. And then we are going to place that color at that XY coordinate. So very simple. This is something that all these computers do, any modern computer can do. You could do this on a giant multi-megapixel bitmap if you wanted, and doing it with millions of colors to get a really nice looking fractal, but of course we can't do that with an 8-bit computer, not even a dream 8-bit computer. So first, let's take a look at probably the easiest process for doing that, because of its dreamlike capabilities, is the Commodore X16. And we're going to do all of this in BASIC. This video is just round 1. We're going to be doing this with BASIC, and we'll talk about what some of the later rounds are going to entail. So for round 1, for Commodore X16, very simple BASIC program to generate this. So we need to clear out the screen, and then we implement the algorithm. Again, very straightforward. The implementation of the algorithm is basically the same for all of them. To handle this iteration, just to make things a little easier, we don't really have a while loop in BASIC, so we have to use a for loop with I, but then we have an early exit. So here, once we see that x squared plus y squared is greater than 4, then we jump ahead here to 215, and we poke that color right into the square that we want to change color. Now, here with the Commodore X16 BASIC, we have the vpoke command. And we can say, here is the address in VRAM, and I want to set the background color to it. Since I did a CLS, or actually I did the screen 0 in this case, the screen 0 command effectively does the same thing as a CLS, where it clears the screen, and it's blown it up to be in 40 column mode, so that it we're not just making a little tiny chunky fractal in the corner. We're letting it take up a fair portion of the screen, make it look a little more like how the Commodore 64 is going to look. So what we do is we're using the basic default video configuration for the Commodore X16, which is at the very top of VRAM at 0 is where the bitmap starts. And so you have alternating bytes for when you're in text mode. We're starting here in 16 color text mode. So the first byte at the very beginning at address 0 of VRAM will be the character code put in there. We're not going to change the character code. What we care about is the one after that, which is the color code. And we want to get the color that we've come up with into the upper nibble of that byte, because we want to change the background color. There's nothing in the foreground. We're just going to change the background color. So we have an I, a integer, because we subtracted from 1. The next I could possibly make it, well, have it somewhere between 1 and 16. We want to get it back down from 0 to 0 and 15. So we subtract the 1, and then we multiply by 16 to get that 0 to 15, or 0 to F in hex value up into the upper nibble of that byte, and that will set the background color, and using the default palette. So 0 is black, 1 is white, and so on all the way up to 15, which is a light gray, and we have all these random colors in between, sort of based on the Commodore 64 palette, as we'll see. And then we just keep doing that for each X value in each row. And then you see here we just throw in this little print statement, because what we want is the ready prompt for basic. We don't want this to be generated over all this beautiful low-res fractal we're creating. So we're just making sure that the cursor keeps moving down until we keep going through all these next PYs until we get through all 22 Y positions from 0 to 21. And then we'll exit. So also the nice thing, as you can see here, everything is in all caps. This looks exactly as it would as if you had typed it into the Commodore X16, except here I typed it into Atom, my text editor of choice. So what we can do here at the prompt is run the X16 EMU, the emulator, use the .bas. Say here I have a text file that contains basic code. So go ahead, load that in. You can let the emulator tokenize it for you, and then you can run it. So let's just do that. So it's X16 Mandlebrot.bas. And there it is. You can see that same code that we put in there. Let me maximize it so we can get a little better. There we go. So there's the code that we had in Atom. It's now in the emulator, and we can do run. And now we can see fairly quickly for fractal generation, we can see this happening. Obviously, it's an appreciable amount of time. And as we get into the higher iterations, which we get once we get up to that sort of index 14, which is this light blue, that once we do that, that's sort of the maximum. So here in this black parts, they happen quick because it's basically, we're not even getting through that first iteration before we hit that threshold. So there we go. We've generated a extremely low-res fractal, a 32 by 22 fractal. So that's how long it takes with the Commodore X16. Now, of course, for context, the Commodore X16 has an 8 megahertz 6.5 CO2. Of course, this is an emulation, but this is representative of how fast that processor would be on the actual hardware. Which, by the way, if for those of you not following, if you're not following Kevin Williams at TechSelect, he is right now testing out and working out the issues with the latest prototype board for that. So go check out his channel. You can see the update in the Commodore X16. And you can see how close we are getting to this third version of the prototype, getting those issues worked out, getting the ROM worked out, and then hopefully this could be the last prototype board, and then we get into the initial production and the beta testing, which will be very exciting. And so what we would expect when we have a prototype or a beta system that first comes out, it should run exactly like this, look like this on a VGA monitor. And then you'd see it happen in about this same amount of time. The timing should be pretty close here. So that's the Commodore X16. Very easy, very much made for doing 8-bit computing in the modern era. Now let's go back in time a bit. Let's take a look at the spiritual predecessor of the Commodore X16, which of course is our friend, the Commodore 64. Here it is in Vice. Vice is a very popular emulator for it. You can just do a million different configuration options with it. Here I have it in NTSC mode, and I've made everything nice and square so that it better matches up with what we see in there. And I took out all of the scanline nonsense. It's like if I wanted to run it on a CRT, I'd hook it up to a CRT. I'm kind of over the way things looked on a CRT, or at least in terms of a television and not like a real computer monitor. I was never really a fan of using an actual computer on a TV. It's just, yeah, that's not what they were made for. So let's go back to Adam. So there was that basic program we just ran on the Commodore X16. And here's the basic program for the Commodore 64. For the most part, it's very different. The first thing you're going to notice is that all the letters are in lowercase. Well, the nice thing about the Vice emulator is that you can do a copy and paste. So you can copy a bunch of text and then paste that into the emulator as keystrokes. Now, if you did Shift before any letter characters, like as you see here in Vice, say if I do Shift whoops. If I do Shift HELLO, I get all that character gobbledygook because we're still in the graphic character set. And if I don't hit Shift, I get capital letters. So when we take these lowercase letters and paste them into the emulator, they're going to show up as uppercase. So a few of the changes that we had to make for from the Commodore X16 to make it Commodore 64 compatible, besides making all the letters lowercase, we don't have the CLS command in the Commodore 64. So instead we have to rely on some of the control codes for the Commodore 64. Nice thing is those control codes are exactly the same on the Commodore X16. So if you're going back and forth between the two of them, it's less of a hassle. So this is a very well understood character set, the Petsky character set. It's used in the Commodore X16. So it's like, hey, I want to do something in Commodore 64, but I want it to be easier to use and I want it to be faster. The Commodore X16 is a very logical next step. So instead of a CLS, I call this, I do print $, which is the control code, and I pass that 147. And that will give us the clear screen Petsky control code. So there we go. That will actually clear the screen for us. So we just have to, actually type out the command instead of just doing CLS. So a few more keystrokes, but ultimately the same effect. But then we get into the code. The rest of this code, for the most part, is exactly the same from line 100. In fact, even you'll see here from line 100 through line 240, I've got most of the same. Actually, up to 220, I've got it the same. So through 215, it was that breakout for the loop. So if we're not going to do all the iterations, we break out and go to 215. And so we have the same thing here at 215, where we do a decrement of I. And this makes sure that our lowest color code will be 0, which is black on both the Commodore X16 and the Commodore 64. And then for the Commodore 64, what we can't do is just set the background of a color. So this the print care 147, it did clear out all of the character codes in the screen RAM, but it didn't. It doesn't let you in the Commodore 64. It doesn't let you just go and change the background color at every single character location, at least not easily and not efficiently. So what you have to do is select foreground colors. But since we can only select foreground colors, we need to poke in new character codes after we do the CLS, after we do the print care 147. So our first poke is actually going to be that. What we're going to do is say here at the screen memory, the character, because we're using the default screen mode for the Commodore 64. And so at 1024, at that address, that's the beginning of the character codes that are going to appear on there. And this, as you notice here, this is just poke. It's not vpoke. There is no vpoke on the Commodore 64 because there is no separate video RAM on the Commodore 64. It's just mapped to regular RAM. So we can just do a direct poke into memory. And so 1024 is our starting address. Of course, this is a decimal address. Commodore 64 is not really friendly with hexadecimal addresses, at least not with the standard ROM. So then we then add this Y coordinate and multiply that by 40 because we're still dealing with a 40 character wide screen. So we to get to each row, we still need to multiply Y by 40. And then we just add the X coordinate so that we go in the a number of spaces. And there we poke in the character code 160. And 160 is the reverse space. So if you think about the ASCII code for space, which is 20 hex or 32 decimal, and what the Commodore 64 PETSCII character set, which you also have in the Commander X16, is you're setting that high bit and you're getting the reverse video of that character. Or effectively, you're adding 128 to get the reverse video. So when we add 128 to 32, we get 160. So that is the all foreground, all the pixels in that 8x8 square will be foreground. And now we can set that foreground color in the color memory. And the base address of the color memory is in decimal 55,296. Again, it looks a lot nicer as a hex value, but for Commodore 64, we got to stick with the decimal. And but then the same thing, it still is the same sort of addressing within that. We're just going each row one at a time, 1 byte per row. And we're just putting something into the a value into any value into the lower nibble will result in the standard default 16 color palette. So we've already decremented I by 1, so we're going to have something between 0 and 14 in here. So we'll get from black up to that same sort of light blue color. If we had gone all the way up to 15, we could have gone all the way up to the light gray. But here we just have up to the light blue. And so we just put that value of I right in there. We don't have to multiply it by anything. It's going in the lower nibble instead of the upper nibble like we had with Commander X16. So again, you can see here the value we're poking, we're multiplying by 16 to get it into that upper nibble. And then the rest of it is also still very similar. We still are finishing up those for loops for PX and PY. And then we have one more for loop because our cursor is still up near the top of the screen. So if we just do this down cursor, the character code here, the control code, which is 17, if we just do 10 down cursors, and each time I do a print down cursor, it's going to do a down cursor and it's going to hit enter. So and then when I return, it's going to skip a couple lines and blah blah blah. Once you get through this for loop and doing all of these print cares of the down cursor control code, you will get the nice ready prompt underneath the bitmap that we just generated. So let's see what that actually looks like. And so what I need to do here is copy all of this code, and then in Vice I can paste it in. Since the Commodore X16 was so fast, I didn't even bother timing it. I knew there was not going to be any chance that the other two were going to compete with it. But here I'm going to actually run the stopwatch, and we're going to see exactly how long it takes the Commodore 64 to go through and run this, because it's going to be a lot slower. So let's try running right now. I'm going to hit the stopwatch at the same time that I hit the enter key. And yeah, we can see already much slower than the Commodore X16. We are dealing with a much slower computer after all. This is a roughly 1 megahertz 6510 as opposed to an 8 megahertz 65CO2, which we have with the Commodore X16. So yeah, it's just gonna take a lot longer. And yeah, so what we're gonna do is just fast forward through this, and I'll let you know how much time actually passed. I'll come here in the middle and we'll say that one thing you can definitely notice here with the Commodore 64 compared to Commodore X16 is the real difference for the number of iterations that you have to execute for each of these colors. And you get a real feel for how long it takes to generate each of these 15 colors. How the black, it's not like instantaneous like the Commodore X16. You can see those black squares getting filled in one at a time, but it's very quick. But then you can see by the time we get to these light purpley ones where we're going through the maximum number, all 15 iterations, it's a very pregnant pause between each one. And we can see those pauses just get bigger and bigger as it goes through that palette. So all right, let's keep this rolling. Let's zip right through to the end. All right, 3 minutes and 23 seconds is how long it took this very simple bitmap to get generated. It's not even really a bitmap, it's just backgrounds of characters. So, or really foregrounds of characters for the Commodore 64. So let's again take a look, just reminded how quick the Commodore X16 can do it. Let's time that one. Yeah, you can see much quicker. Here we are, we're at 5 seconds in, we're almost halfway done. So it's going to be significantly faster. It's not even going to be just 8 times faster. All right, here we go. And yeah, so 22, almost 23 seconds. So yeah, it's yeah, you're looking at, so what, that's except no, okay, so maybe about 7 takes about 7 times longer, 7 to 8 times longer. So it really is, since we're dealing with the same kind of basic, and also have faster memory access for the colors, so we do get a bit of a performance boost with the Commodore 64 for that. We're not having to go through this VRAM bridge that the V-pokes definitely take a lot longer to do than the pokes do, at least in terms of the number of cycles, but each cycle is happening in 1/8 of the time with the Commodore X16, so you more than make up for it there. But there we go. We've got all that. Now, how do we do this in our friend the Sinclair ZX Spectrum? So again, remember in Vice, we could just copy and paste. And here, I'm going to just kind of put these off in the side to remember what they look like. So there we go. These two beautiful fractals. How are we going to create something equally as beautiful in the Sinclair, in the ZX Spectrum? Well, we're definitely going to have a very different color palette. We're not going to have all of these earthy kind of tones. We're not going to have the purple brownish thing happening like you get with the Commodore. So let's take a look at how we would do that. Now, one thing we definitely can't do is just write it up in our text editor and then paste that in. That's not how it works, at least not with this emulator. I can't just paste in keystrokes. Again, because the keystrokes also are very different, especially when you're dealing with the 48K Spectrum. And everything I do for the Spectrum, I try to reach the lowest common denominator of what is, in effect, the lowest common denominator of our little battle royale that we're having here. So I have to be able to input it as tokenized basic. And so that means just doing it within the emulator. I'm not going to do that in real time. I have a snapshot where I already did it. And here it is. So let's take a look at this code. Now we're going to have the Commodore 64 up here for comparison. And you can see that, again, a lot of the code is the same, but it's sort of in Sinclairese. So we do have, like the Commander X16, we have a CLS command. We don't have to print some control code, although you do have control codes for the ZX Spectrum, but you don't have to worry about it for the purpose of clearing the screen. There is an actual CLS command. And then one other bit of work we want to do ahead of time is define our colors. So what we don't have with the ZX Spectrum is a 4-bit color index into the palette, because we don't have a proper 16-color palette. We really just have that 15-color palette, like I mentioned before. That's why we're only doing 15 colors, because you do have you have 3-bit color for the ink and paper, and here we're just changing the color of the paper and eliminating the ink. So another nice thing with the Spectrum is that we don't have to print a bunch of blocks. We can just leave the spaces that are left behind by the clear screen, but then change the background colors for all of those spaces. But for those background colors, we only have like 3+1 bits for those background colors. So we have 3 bits to determine the color, and then a bit for brightness. And the way the brightness bit works, of course, if you've been following some of this stuff with the ZX Spectrum, is when your color value is 0, meaning black, a bright black is still black. So when you just have 0 for the color, it doesn't matter what the brightness bit is set to. So it's only the other 7 colors that you can have in there from 1 through 7 in that little 3-bit field. And then you can set the brightness on or off, and then you can get the different shades of the other 7 colors. So to do that, we're going to build an array here in our program. So that's what this dim is doing. So we're creating an array called C with 15 members in it, 15 elements. And then we do a for loop of 1 to 15. And we're going to read from standard input a value to place into this C array. And then that's the end of our for loop and next end. And then to feed standard input, instead of having the user just type in stuff from the keyboard, we're feeding it in right from the basic interpreter by doing data statements. And so here are the actual values that we need to put into the color attributes in the screen memory of the ZX Spectrum. So 0 is, of course, none more black. But of course, if we put in, 64, 64 would still be black. So that's why what we have is basically every 8th value except for 64. So we go from 0, 8, 16 on up to 56. We skip 64 and go right to 72. And then all the way up to 120, which will give us the bright white color. And that's it. So we've now filled out this 15-member, 15-element array called C to have all of the color attribute values that we're going to put in there based on the number of iterations. And then, of course, the rest of the code goes as you expect. So we've got these for loops. Now, a limitation for the ZX Spectrum for Sinclair Basic is that loop indexes can only be single character variable names, which is super annoying. One of the many annoying things about doing Sinclair Basic, aside from the fact that you need a cheat sheet to know how to type in things like for and data instead of just typing them out. Now, if you did have a later version of the Spectrum, you could do that, but I wanted to have Spectrum 48K compatible tokenized basic. So I just bit the bullet and went ahead and did this in the 48K mode. So we can't use the PX and PY for our main loop indexes. So we do just Y and X. But the same thing, Y is going up to 21, X is going up to 31. So that covers that 32 by 22 range. So now, of course, with the Spectrum, you can go up to 24 rows. But what's going to happen is after your program runs, the Spectrum Basic, when it returns, is going to basically clear out the bottom 2 rows. So we're not going to bother filling them in, which is why we just did 22 rows for everything. Because why bother doing those if you're not going to be able to see them a millisecond later? So now we've got our nested for loop, and God forbid in Sinclair Basic you actually start a basic command with just a variable name for an assignment. You have to use the let keyword. And again, the let is just another token that you have to do the right keystroke to put in. So we do all these lets, and then we get into that third level of a for loop for I. Luckily, we are already using I, so that makes it simple. And then we can have the same if statement here that, again, still at 170, and it looks still exactly the same as our Commodore 64 and the Commodore X16. And then we do these assignments. We get the new values for XT, Y, and X. And you notice here for these internal X and Y values, I just call them XX and XY to differentiate them from the loop indices. So kind of reversed is how I was forced to do it with Sinclair. All right, so next I that ends that third level of the loop, and then we have our poke. Now here, let me go back up to that. So our poke for the Sinclair ZX Spectrum is going to be different, of course, than the Commodore X16 or the Commodore 64. So with Commodore 64, our color attributes started at decimal 55,296. With the ZX Spectrum, it starts at 22,528. Again, just magical numbers, especially in decimal, but they're nice round numbers in hex. So it works out. But then we're doing the same thing where each Y value, we want to skip to the next row. But here our rows are actually 32 wide. So we multiply 32 by Y and then add an X. And that will get us the position of that color cell that we want to change. And then we just do CI. You notice one thing we omitted here is that 215. It is kind of interesting now, I'm just noticing, is that it doesn't need 215. It just says, oh, there's nothing at 215. I guess I'll just go on to 220. And so at 220, I have to dereference that array with a 1-based index instead of 0-based index. So that's why I don't do the decrement of I in this. And then we just do the next X and next Y. So we get out of the for loops, and that's it. That's all there is to it. So we're going to run it, but of course we need to get their stopwatch ready. So I just do run. Only have to type R. Luckily, I know that it's R. And then we're going to time it. Go. And we can see here the time is kind of similar to the Commodore 64. Of course, it's not like 3.5 times faster if you were looking at it as, oh, well, the Spectrum has a 3.5 megahertz Z80 in it. Certainly that's going to be a lot faster than a 1 megahertz 6502. Well, not really. So a Z80 requires a lot more cycles to do basic things. And in terms of this basic interpreter, it's not the Microsoft BASIC. This is a different version of BASIC that Sinclair had made for its platform. So the source code for it's entirely different because, again, they couldn't just use a 6502. Microsoft didn't make a Z80 specific BASIC that they were able to use, so they have this different one. And yeah, so it starts out fast, but once we get into the big thick white part, which is the maximum number of iterations, it's definitely taking a long time for each of those squares to happen. So we're going to fast forward through this and we'll see how long this takes. So see if we can beat that 3 minutes and 23 seconds. I'll put up the actual time on there because my memory is only so good. All right, let's get it going. All right, so just for comparison, we are approaching the midway point of the, we're at midpoint now. We're at 2 minutes and 22 seconds, so it's not looking too good for our friend the Specky here. It looks like it's going to take longer than the Commodore. Let's keep her rolling. All right, looks like we're coming about to the time where the Commodore was already done. So from here on out, we are now just on pure Sinclair time. So come on, Specky. You can do it. All right. So 4 minutes and 33 seconds. So more than a whole minute longer to do it, which, not great. But, it still works. I mean, we still generated a fractal with another 8-bit computer. And arguably a much simpler and lower powered computer, especially when you compare like the graphics capabilities of the games for it. So there we go. There's our 3 fractals, all very different and in their own special way. And I know, which one do you think looks the nicest? And this is certainly a purely subjective. Obviously, the Commodore 64 looks very, earthy and muddy compared to the others. The Spectrum, of course, is loud and garish, and the Commander X16, I think it makes a nice little, nice in between. Of course, the other big advantage for the Commander X16 is if you don't like those colors, you can change them to whatever you want. You're not stuck with any colors whatsoever. So that's it. Now, what we're going to be doing, let me zoom in on here. We're going to be just getting a whole bunch of more different ways of doing this Battle Royale. This was only the first round, and obviously the Commander X16 is the winner on speed, and the last one out, which of course is the bad thing in this version of a Battle Royale, was the ZX Spectrum. But we're not done. So the next round will be in assembly because, again, we're dealing with BASIC, and BASIC is kind of slow. Now, we are doing a lot of floating point math, so obviously it's going to be slow, and we're going to have to sort of re-implement that in assembly language. But I don't think we necessarily have to use floating point. I think we can do a fixed point solution that is going to work on both 6502 and on the Z80, and we'll get something that generates these fractals a lot more quickly. So that'll be the second round. That's coming up. Of course, the best way to see what's coming up is to join our Patreon community. And so we're going to bring those folks up right now. And so if you join up on Patreon, you can see the next video before it goes out to the public. You get to see it ad-free, and that can cost you as little as $1 a month. Of course, you pledge more, you get even more awesome rewards. And be able to be a part of the inside track on the things that I'm doing here on YouTube and the games that I'm creating. Get a little more behind-the-scenes action. And so what we'll see in the next episode is that assembly language version, and maybe in future episodes trying to do a higher resolution fractal in these. Of course, with the Commodore X16, we can do a very nice 640 by 480 256 color rendering of a fractal. It'll just take forever. It'll take probably several days to do it. But you know what? That might be a fun experiment. So we'll see what that looks like. And but then we'll do this in some different ways. We'll do, I say, at least 2 more rounds of this battle royale, and we'll see just how difficult it is to do these calculations, how long it takes, and maybe some of the benefits of using some platforms over others when you just really want to solve a difficult mathematical problem using the most primitive tools possible. Again, if you didn't want to do that, I don't know why you're here. So please, if this is the kind of thing you like, go ahead, like this video, subscribe, let me know what you think in the comments, and if you really want to get involved, hit me up on Patreon. All right, take care. Bye-bye.